Okay, hello everyone. I believe we can start today. Yep. So today we are not streaming from terrace once again because the weather is not that great, I would say. Hi everyone. Thank you for joining. It's today will be a late office stream after work, so cannot say that I'm so fresh, but anyway. As you all voted in the Telegram, right, and Instagram as well. By the way, the topic for today, and the vote actually was to make more topic-based streams, and this is what we're gonna do today. So currently, my team at Microsoft SWE are heavily using the Redis. So the system design would be, since we are covering sharding topic quite a lot, so we're gonna cover consistent hashing, then rendezvous hashing, and also for sure we're gonna cover the Redis sharding in the end, how it works. It's not either of them. It's not rendezvous, it's not consistent, and it's pretty simple to implement. So we're gonna system design it. This is the first stage, and next stage for the next streams we're gonna implement it as a POC for you. Also we have kind of backfill for the Redis, as it is open source, right? So we can check how it is legit implemented inside the real production code. So I guess we're gonna start. We can also check and maybe solve some legal questions if you want it in the chat, because we still didn't finish this 75 list. However, I finished it a long time ago and I don't really need it anymore that much. So right now my lead code consists of just doing daily, and that's it, to keep the skill. If you want, we can solve a bunch of questions in lead code, but the topic for today is Redis sharding, how it works and stuff like that. So what we're gonna do, since you see your vote actually affects the decision for the topic of the stream, so please don't forget to subscribe to the Telegram channel. All links in the description, and also don't forget to subscribe on Instagram. All updates are here. Actually, great news are coming in the future. There is something going on, so I will keep you posted later, but for now I can't reveal much. So what about the system design and Redis sharding, and why do we need sharding? What is Redis? So for those who are not familiar, Redis is a distributed cache. Which means that it is cache that is not on the single node, so it can be spread on different nodes. And mostly what we need from the cache and from the distributed cache is that we can, for the cases when we cannot fit all data in one node, we want to have multiple nodes. So this is exactly what sharding is about. So sharding, let me draw it a bit. Boom. Oh, shit. So we have our one node, let's say. So for all of you who doesn't know, Redis is one-threaded cache, and at first glance it might look like it's a big drawback, right? Because how come the storage can be one-threaded? How come it can then support so high RPS and stuff like that? If you consider any SQL database, they are all multi-threaded, right? Because you cannot just handle it all in one thread. But Redis is the cache, so mostly it is working over the memory, and it means the operations are in general fast, because you might configure it in a way that it does not go to file system at all. But Redis also has this append only file, AOF, something like wall, in the typical SQL database. So you basically have some append only file and this log, whatever, and you push all the operations that you're performing there. So even if Redis crashed, you can recover from this log and you don't lose your data. Yeah, that's about the Redis. But yeah, let's talk a bit about being one-threaded, because we're gonna implement it, right? And when we're gonna implement hash slot sharding, yeah, we're gonna implement it also one-threaded, just for the sake of being consistent with the actual Redis implementation. So yeah, Redis uses hash slot sharding. Yeah, this we're gonna talk about a bit later. So yeah, why it's one-threaded and why it's not a problem. So first of all, yes, since Redis operates over the memory, the operations in general are very fast because you don't need to go to disk. This is first thing. And one thread, yeah, it actually, as a drawback, it slows you down, right? You cannot do things and stuff in multiple threads, and it seems like a very bad. But contrary, and from the other hand, on the other hand, the one-threaded mechanism actually protects you from a huge amount of problems. And you know these problems, for example, if you read this Martin Kleppmann's book or you saw his lectures or something like that, you already know that concurrency is a problem. Concurrency is a problem, and you should be very careful with handling the concurrency. Otherwise, you can get data loss, you can get data integrity breach, so your environment in your application and in your data breaks and stuff like that. So why it happens? Because yeah, whenever two threads try to access and modify a single piece of data in memory, it's usually a problem. And Redis doesn't have this problem because it executes everything in serial order. You can think of this as in having serializable isolation in the SQL database whenever every single operation is happening in the sequential order, and this means the operations are atomic. So once they are kind of wrote into this append-only file, or once some in-memory variable is updated, it's done, and no two threads cannot access and modify the same piece of data. So this is a very huge advantage, and it's very feasible for the cache because yeah, in general operations that are fast. But talking about this in scope of one node is still kind of, you know, it might not be enough, and usually one Redis node is not enough. Imagine, yeah, you're pretty fast with the operations, but still you might have like thousands and thousands requests per second, and it might not be enough still for your use case. Or you have huge data load, right? But not that huge RPS. So what in this case, usually what databases are doing, they are applying sharding. Important note, don't misuse term sharding and term replication, because replication is mostly defensive availability pattern, so it protects you from losing the data whenever on the other side, the sharding, it doesn't protect you from losing the shard. So I might have only the sharding but not replication, like in this case, and it means that like this shard would handle some data from range 1 to 100 or keys, whatever. I'm not talking about Redis, it's in general. Like let's say I shard and split my data into 3 pieces and move these 3 pieces around these 3 nodes. If I lose this node here, sorry, actual case would be 100, 1, 200, and 201, 300. So if I lose this shard, actually there is no protection mechanism that sharding is adding to you. Because sharding is not replication. So if you lost this shard and you have some load balancer here that kind of decides based on key where it will go, it doesn't protect you from the fact that you will not be able to access this range of the keys. So just something to keep in mind. We are not tackling problem of replication here. We're tackling only the problem of distribution of the load and distribution of the data. So let's now think about how Redis sharding is working, or not even think about. We can go straight away to source code actually. Let me find for you the source code, and we're gonna check how it works from the inside, right? So the source of truth basically. So let me find my notes about the distributed system. Yes, so yes, exactly. Yes. So let's check the doc, and this is basically my doc that I'm having for the system design. So let's check how Redis sharding works, right? So Redis, what is he doing? What they decided to do for the sharding, comparing to consistent hashing and rendezvous hashing, like how is it different? So Redis basically, they are also based in some way, based on some numeric area, whatever, ranging from 0 to some number, and they just basically pick some ranges and assign these ranges to specific node, right? So this is gonna be handled by this node, this is gonna be handled by another node, this is gonna be handled by this node, and the last range is this one, handled by a separate node. And then we have some deterministic algorithm that, based on, I don't know, this number, I don't know, k, let's name it k, it can apply some hashing or whatever it is, some function on top of that will give it a shard, and this shard is like from this, oh sorry, it's gonna give you actually hash, and from this hash we can understand, okay, if this hash lies here, we go to this node, if hash lies here, we go to this node, and stuff like that. I hope this is pretty much understandable, and this is how consistent hashing works in a way, but consistent hashing usually, it splits the numeric arrow starting from 0 to some max number. Usually it's 3 to the power of 32, oh sorry, 2 to the power of 32 or 2 to the power of 64. So it's either int, long, or long data type, and they arbitrarily or randomly assigning the nodes to handle the previous range. So for example, yeah, this will be the first range that this guy handles. This range is handled by this guy. This range is handled by this guy. And this range is handled by that guy. And now we deterministically can say that if some key lies here and falls here, we know that this guy is responsible for this node. We have some data structure, we can use some binary search, whatever, to find this node and go and send requests there, right? So this is pretty much about the consistent hashing and how the Redis sharding is different from consistent hashing. In consistent hashing, we are using some upper bound here. So usually it is represented as a circle, but in a nutshell, if you flatten the circle back like this, you will get this numeric arrow, right? And hash slot sharding is pretty much the same. So Redis claims that they have 16K384, as I'm not mistaken, 384. Yeah, 384. So this is the number of hash slots. Okay, let me actually write it down for readability. 384 hash slots. Exactly. So this is the thing, and they starting from 0 or from 1, I guess from 0. And now what is going on? You can treat the hash slot is already kind of a virtual node on the physical machine. So in a nutshell, it's pretty much the consistent hashing, but it doesn't work with the ranges as it works in consistent hashing. So let's say we have this number of hash slots, and we have right now one machine. So all these hash slots are handled by some specific node. So let's say by this node. Cool, cool. That's cool. Now, what if I want to add key or read the key? So I'm applying some algo, and this algorithm actually is called CRC16. This is for checksums, but Redis uses it to detect the hash slot. So I'm applying this guy to key. Let's omit the fact that Redis has specific treatment for curly braces. So if you have this key, only this part of the key will be used for calculating the hash slot, basically. So let's say we got some key, we apply this algo, and in the end, what we received, I don't know, some hash. And now, based on this hash, we can do this. This kind of anti-pattern for sharding in general. So in general, if you just have some number of nodes, let's say 5 or 6, you never want to apply modulo operation over the number of instances. Why? Well, because we actually discussed this on the previous session, that then adding new shard will be a huge pain for you. But in that case, Redis is doing exactly this thing. So it applies modulo operation over 3, 8, 4. So number of slots. And this way, it has the slot ID in some sense. So the resulting number after this operation will be the slot, basically. Or can you see actually? Yeah, you can see the screen. Yeah, so far it a bit seems like the consistent hashing, but the differentiation is that in consistent hashing your key might might fall on some range, and it is not usually the ID of the node, or this slot ID is usually just inside some range. In case of hash slots, your key always falls to some specific hash slot, and it goes to some specific hash slot. Now, how Redis actually operates over this hash slot? So it's pretty simple, since 16K is still a constant. Redis in general has this structure, so it has map, or rather it is array actually, but it still would work like map because yeah, it will be result in constant. So slot ID is basically gonna be from 0 to 16K383. So by this slot ID, I can in general take the node object in memory that is actually handling this slot, right? And what will happen then, that, okay, let's say this node has this map. So right now this map has exactly 16K blah 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 keys at the moment, because all slots are handled by single node. It's not sharding yet. So yeah, we got the key, we calculated the slot ID, we put this key to this node object. And node object in general, node object, let's say it has some key value pair for the as a actual cache. So in this case, if this is key 1, I'm gonna go and check this is key 1, and I can assign value here or read value from here, depends on operation I want to perform, right? Redis has multiple data structures and multiple operations to perform. So this is basically how is it performed, and it's pretty simple if we have one single node. So again, recap, we have map contains all the hash slots. Hash slot ID is calculated based on this formula, so we're taking hash based on CRC16, and we perform modulo over this over all the hash slots, right? we go to this specific node object and we have mapping which slot is handled by which node object, and node object basically has the key value mapping. Now, let's say I cannot fit all the keys in this single node and I need to scale, or I cannot handle the request per second on this specific node and I need to scale my Redis cluster from 1 node to 2 nodes. How do I reassign all the keys that I have? So again, alternative, consistent hashing. Let's say my node randomly generates here and I'm handling all the way keys from here and from here. So this is everything I'm handling. Basically all the numeric space I'm handling. And in case I want to split in consistent hashing, what I would do, I would add another node here, right? And now all this range gonna be handled by node 2. This, let's say this is node 1. And this range is going to be handled by node 1. This is how consistent hashing would work, and we're gonna migrate only kinda this amount of items, right? But it's not the case in the Redis hash slot sharding, because we don't actually operate on the ranges, we operate on the hash slots. So the solution here is to basically reassign hash slots. So right now how it works, let me draw you a bit smaller example. So let's say this is a numeric space and we have a bunch of hash slots here. Let's say like this. Yeah, sorry for my drawing skills, but let's say these are hash slots and each hash slot corresponds to some, as we told, node object node, and it has all the cached data. So before that, we didn't introduce this guy yet. We had only one single database or Redis shard, whatever, and it was handling all of them. Or rather, I would draw it like this. So this is mine, 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 and this is mine. And it's so on. So it handles every single one of them in this map. Now, what will happen the next? I'm not if you're familiar with Redis, but resharding is happening manually. So I'm not sure in the default vanilla Redis you can do automatic resharding and rebalancing, but there is specific command when you manually can reshard. So how it would look like, that I would connect to this guy, to this node. I would type, okay, reshard this node. I would point this IP of this next node, the target node, and this is the source node. And I would select specific shards that I'm gonna to move here. And that's basically it. That's basically it, how it would work. So, how it would look like, let's say I want to move just a bunch of shards. So what I would generally do, I would initiate this manual resharding process, and I would claim that, okay, this guy, and this guy. So I randomly can pick whatever items I want. It is not a problem for Redis. Like the hash slots that node is handling, it doesn't have to be contiguous. Not like in consistent hashing. And this is what actually differentiates hash slot sharding from the consistent hashing. We don't operate over the ranges. We operate over hash slots. So since it's map, we can arbitrarily move in any slots that we want. And it gives a lot of flexibility in this case. It gives like a huge number of, huge amount of flexibility in some sense. So let's say I migrated these slots here, and now my map would look like this. So let me name, this is node 1, and this is node 2. So how it would look like in the memory of node 1 and node 2. Actually, let me do this. Yes. Let me remove all the unnecessary thing here. So how it would look like at this point. So node 1 inside it, it has some cluster information. In this cluster information, it has, first of all, hash slots and hash slot map. Let me draw it like this. So this is the first, this is second, third, fourth, fifth, sixth, seventh, and so on. So in that case, hash slots array would look like this. It is array, but let's draw it as a map because we don't want to work over contiguous array. So hash slot 1 is actually handled by node 2. Let me do like this. Hash slot 2 is handled by node 1, me. I gotta change it to small one, yeah, otherwise it will not fit. Okay, so let me put it like this. Exactly. So hash slot 2 handled by node 1. As you can see from this mapping, hash slot 3 is handled by me again. Hash slot 4 is handled by node 2. Hash slot 5 is handled by node 2 again. And hash slot 6 and 7, node 1, me again. 7, node 1, node 1, me again. Now, how it will look like for the node 2? Exactly same, but we're gonna just remove me to not me. So this is going to be me, and this is going to be not me. This is me. This is me. Because node in general can understand is it itself or not. So do you see like the configuration looks pretty much the same and mapping is exactly the same? The thing is that, yeah, let's say the request appeared. Okay, so let's assume now this thing. So let's say I have some keys and I'm gonna write them here. So let's say I have here for hash slot 2, I have key 1 with value 1. And also I have here, so me, yes. And this guy is handled key 2, value 2. Something like this. So this is what we have in our database. So node 1 has value key 1 with value 1. Node 2 has key 2, value 2 in hash slot 1. And this guy has it in hash slot 2. Now, let's say I'm the user and I want to read the key. And I want to read the key 1. I'm again go and follow this process. I'm calculating the this hash of the key, get the slot ID, and since key 1 is here, the hash slot for this guy deterministically would go and be in the slot 2. So let's say I went to this node and actually I read it. And yeah, I just straight away returned it as a value 1. Easy peasy. But what if, contrary, we have the following situation that there is user and it wants to read key 2. And it went somehow to this node because, I don't know, load balancing, whatever. How then request is going to be redirected to this node and how we actually know it and what will happen in general. So I want to get a key 2 and I landed on node 1. Node 1 goes, calculates the hash slot, realized that hash slot for key 2 is actually 1, this guy. And he sees that node 2 is not itself. So it shows that, oh sorry, it returns the status, something like move or moved, with the IP of the node or any host name of the node that actually has this key. In this case, it's going to be node 2. So now client goes here. Same hash slot gives, same key gives you same hash slot, but now this hash slot turned to be handled by the current node, and we return value 2. This is how in general it works, and this is the all hash slot sharding explained in a, I don't know, dozen of minutes. So yeah, now how do we maintain the configuration? How do we, for example, omit split brains? So whenever we are moving shard, we are putting these specific hash slots that we're going to move. Let's say these 3 guys that we wanted to move to node 2. We put them to specific state that in migration state, and then also we are doing consistently gossip protocol here. And gossip means that we are randomly choosing some small portion of the nodes and sending ping pong requests to them with the current configuration state, with the current cluster info basically. And they have cluster info version, which is like monotonic sequence number, and due to gossip protocol, the configuration is getting propagated without some coordinator or something like that. And it happens pretty fast, and we don't need to send requests to all of the nodes to not generate n to the power of 2 network calls. Instead, gossip would do it pretty fast and efficient as well, but in the end, yeah, producing only up to all WAN calls, right? So this is basically it. This is basically it. So yeah, I guess this is all that is related to Redis sharding. We're going to implement the same thing, and let's actually check the implementation in the source code, right? So yeah, let's go one by one, link by link. So this one is kind of proof how many hash slots do we have. So if you move bit 1 to 14 bits to the left, it will give you exactly this number of hash slots, which is basically true information. So this is the maximum amount of hash slots. Redis cannot extend the number of hash slots. Why? Because it uses this modulo, and it will cause extremely bad influence and bad consequence of resharding, especially having in mind that our hash slots can be distributed randomly on different nodes, right? So this is kind of we already confirmed from the source code right now. Great. So now, yeah, let's check how the hash slot ID is computed. It's exactly computed like that. So key hash slot function name, key hash slot. Exactly this guy. So they left it in the comment. So we have this number of hash slots. Given key is obtaining at least significant 14 bits of this hashing. Yeah, and they also specifically handling the curly braces pattern, because only this one gonna be used for the detecting the hash slot. Pretty simple. We are running this guy. Yeah, now we are handling just the curly brackets, and that's it. And we're returning it, and that's it. That's it. Pretty easy. What does this mean? I'm wondering. Yeah, this is exactly the number of hash slots. It's just a hexadecimal representation of this number. Great, so this is how we define a hash slot ID in the official Redis source code. And now let's check the cluster node kind of class or something like that. Cluster node. So cluster node. Yeah. So this is the struct or class that is responsible for specific node, specific shard. So every specific shard and node, it has shard ID, name, blah, 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 some flux, configuration epoch, which I was talking about. It's kind of monotonic. It is used for gossip protocol to understand that some node, for example, send you very outdated configuration epoch and you don't want to apply this. This is actually something interesting because you might be asking, like, why cluster slots is this number 16384, and why do we allocate array 8 times less? Because they are using, instead of mapping and instead of array even, they are using bit checking. So what did they do? They are using so let me draw it actually. So they have 16K options, and they want to use as less memory as possible to detect whether the specific slot is handled by current node or not, or this specific slot is handled by some other node, whatever. So for this situation, how do they do and how you can check it quicker and using less memory, 8 times less memory actually. You can allocate the number of bits starting from 0 to 16K, and basically y divided by 8, because you need actually 16K bits, which can be divided by 8 to realize how much how many bytes is it, because every byte might have 8 bits, right? So it means, yeah, that's why it works, but vice versa. They don't want to have array of bytes and represent each byte as a separate hash slot. So instead, they are representing every single bit as a slot ID, basically. This is only memory optimization, so don't be worried. It still represents whatever it is. It's not like the node handles only 1/8 of the hash slots. No, not still. Every single cluster node handles all the cluster slots. So, node slots. Yeah, and then there are a bunch of stuff. Slaves are actually replication concept we don't care about at this particular, I don't know, stream. Ping pong, these are the times for gossip protocol when it was last time performed. Replication of set time, this is a replication delay, also replication not sharding, we don't care. IP of the node. Host name, so from these guys node can basically understand that it is itself or it should redirect the request to another node. Yeah, and bunch of other stuff which is pretty much MISC in this case, and important stuff are these like slots and yeah, basically slots. Now let's move forward. This is what happens in a single cluster node, but what is, yeah, this class is, it represents only the single shard in the Redis cluster, but there is class that represents the whole cluster, and this class it actually has, so how is named cluster state, yeah, and this struct or class or whatever, it actually is presented in every single shard as well. So this data structure is not like located in some specific coordinator. No, every single node cluster, every single shard has this cluster state in itself, and they just syncing it via gossip protocol. So this guy also have like current epoch, which is kind of configuration epoch. Nodes, this is cluster nodes. So this is dictionary of these guys. How many shards and blah blah blah. These things are used for migration of the slots, these hash slots, And also we have here our slots as well. So yeah, here are slots and there are slots, but they are represented also as in a cluster. That's basically it for the cluster. Nothing that much interesting here happening. Now let's take a look how I can actually show you from my Google Docs straight away. So how the hash slot moving is happening. I already mentioned that in a vanilla Redis it does not have dynamic resharding and dynamic upscaling and downscaling. Therefore, it works manually. So you need to manually reshuffle hash slots between the physical nodes. And this is how the cluster deletion and cluster appending happens between the nodes. So you have source node, target node. You need to add in your Redis cluster, you need to add the hash slot keys to the target node and remove them from the source code. This is basically how the migration is happening. And of course, it's not atomic operation, so it happens in the phases and it syncs and stuff like that. So yeah, what is going on that we are taking the cluster node of that handles specific slot that we want to migrate basically, and we remove yeah, this is a replication concept again we don't care about. We set that this node does not handle this slot, and yeah, clearing it from everything. And yeah, this is how hash slot basically disappears in a Redis cluster, and this is how we append them. So yeah, cluster node set slot bit, we are setting specific bit for cluster and tell that this node is handling this cluster and assigning this node here, and that's basically as easy as that. Not something very complicated, to be honest. Yeah, and this is ping pong. This is this gossip protocol that is carried by Redis. So basically every node communicates with a random small portion of the other nodes to propagate the configuration changes. And this is basically it. This is the Redis sharding. This is how it works. You can then merge hash slots back. It's not a big deal, right? So let me actually prepare some maybe design, or I don't know how we can even call it. So for our future POC for this sharding, because I think next stream we are going to implement this sharding, or this type of sharding. So what I would assume I most probably would use .NET. We're gonna have some singleton service so that we kind of emulate vanilla Redis flow in the sense that it is single-threaded, so we don't care about concurrency problems in this case, right? So what we might have, we for sure need some, I don't know what it would be, let's name it some shard or whatever. We would skip all the concepts that are related to replication, as resiliency is not something that we are studying here at the moment. So we're gonna have shard, and this shard, what it should contain. So shard is going to have, yeah, let me actually draw it a bit bigger. So this is going to be our shard. I'm not quite sure in the official source code why do we have slots in the cluster state and slots in the cluster node. So this is something I would like to clarify, to be honest. And also, do you see that this guy has only, I don't know, this 16K divided by 8. So 16 divided by, yeah. So only 2K slots are here. But this guy has all cluster state. And I'm really sure that, yeah, both of these states are shared between the nodes. So I will double check it before the next session, but in general, we're gonna have something like cluster state. We're gonna have some node here, whatever. And node is going to handle also the keys, I would say. Right, so I'm not sure still how the operations are performed. Do you have something for this? Cluster node name. I don't see anything here, to be honest. So, but I still would assume that somewhere in this node we have, I don't know, key value pair dictionary, so the actual cache. Key value pair. So this is actual cache in our node. We have our cluster state, yes, and we have our hash slots here as well. And shards are going to communicate between each other. Right. Again, replication is not covered yet. We're gonna implement some API for moving shards out. And let's say we're gonna have third one. So our POC would look like this, that we're gonna move, I don't know, some shard, oh sorry, some hash slot from here to this guy, kind of perform resharding. And via the gossip protocol, we would actually propagate this change to this guy. So this guy in his configuration, he would know that this slot with ID 1, whatever, is now here. And this will be happening on gossip protocol. So in our implementation, we want to implement actually gossip protocol as well. Yeah, resharding, and that would be it. And yeah, we would need intermediate state for the hash slots, because again, back to our picture, how we understand that, for example, if we want key 2, how we understand that key 2 is here in this node. Since we have this cluster information, we go to hash slot and we realize that this hash slot is handled by other node. But the problem is that during the hash slot migration, it might be the case that, for example, let's say we went to this node. Let's say we went to this node, and we see that key 2 is handled by this node. But we go to this node in memory, in this key value pair, and we cannot find it anymore because it is getting migrated here. So for that reason, we would keep same, sorry if it looks like stupid question, if we need to change node counts, we will have to rebalance all the data. No, and it was explained already before, so let me explain once more. Look, why it's not the case for the Redis, because resharding happens in a way and perform in a way that we are not changing the number of hash slots that we have over our physical nodes. We're only changing the home or location where these hash slots are served. So let's say we have our hash slot numbers here in this numeric space, and during the sharding, what will happen that, let's say, node 2 is responsible for hash slot 1. If I want to add one more instance here and rebalance it, so I can, for example, pick this guy and move it here. So I would just migrate this, or yeah, let me, for the simplicity, or sorry, for more real case, I want to migrate this guy and let's say this guy. So what I will do, I will just migrate these hash slots 1 and 6, and I will claim that, yeah, let me change the color like this, yes. And I will claim that, yeah, right now node 1 loses the hash slot 6 and node 2 loses hash slot 1. Now these hash slots are handled by this Redis cluster. And how much data did we move? Already we moved only these 2 hash slots. We didn't touch anything else. So that's why we don't have to rebalance all the data, because the data integrity, in a sense, and actual hash slot count is not changing, so we don't need to rebalance anything. We're just moving hash slots around between the physical nodes, and this is the beauty of Redis sharding. Any tips on getting internship for fall, winter? Is it the company name or you're talking about the season? No, I guess you're talking about the season. Tips, well, I'm not sure. Get the referral. This is tip number 1. Without referral for internship, it might be very complicated and hard. Even if we're not talking about internship, but about regular positions, market might be very bad. But right now, to be honest, I would say that market is much better than it was in spring, for example. Just telling it from my experience, no more questions with this regards. Cannot share a lot. So, yeah, first get referral. Second, since you intern, I don't know, have maybe some cool project, but I'm not sure how it will be working. It would be great to have previous internship in some other companies as a previous experience. Prepare for an interview, so lead code system design. Yeah, you might be asked system design even if you're intern, at least at Microsoft. I think in Google it's not the case. So I would prioritize like 60-70% lead code and maybe 30% for the system design for you will be enough. And yeah, so referral, good CV, maybe some project optional, lead code and system design, that's it. Yeah, but you should be lucky anyway. You should be lucky with the interviewer, you should be lucky with recruiter, you should be lucky with automatic CV analyzer or whatever it is. So every single time you're searching the job and you're applying for something, it's a huge percentage of this is basic luck. Okay, thank you so much. Yeah, no problem. Yeah, good. So this is gonna be our kind of implementation. Maybe one thing I would ask still ChatGPT about the Redis, because since ChatGPT went over the public GitHub repo, actually it knows about Redis. You can check it and ask questions about Redis. So in Redis official open source repo, I have cluster node which has slots array that maps slot to node that owns the slot, and I also have this mapping in cluster struct. Why they are duplicated? And now what I want to, where are, yeah, these are slots. These are slots that handle only by this node. Wait a bit, wait a moment. Okay. Yeah, so maybe in cluster state it's kinda, yeah, these are hash slots that are handled only by cluster node for this guy. And in cluster state, cluster state has slots for all the nodes, and it has mapping from the slot to the any arbitrary node. And cluster node has slots array that is covering only the slots that this node is responsible for. Let's confirm it from ChatGPT. Represents what the given node is responsible for. Okay, a bitmap of slots. Okay, that's why the bitmap works. So yeah, I'm sorry guys. So yeah, that's why they are using bitmap, because when you're working with this cluster node, what you want to check and how you can check whether some specific slot is handled by this cluster node or not. You want to check whether the bit is set or not set. So whether it is 1 or it is 0 in your bit space. And this is how you basically check it pretty quickly. Yeah, this is kind of understandable. Does this node own slot X? How many slots does this node have? Okay, this also is. Okay, and in cluster state, global state mapping every slot. Okay. Is the cluster state replicated to all the shards, or it stays in coordinator? It's just confirmation. I'm pretty sure 99% is replicated to all the shards. Wait. And redundant by efficient when iterating all slots in node. Okay. Makes sense. Maybe not fully, but still makes sense. And now what I wanted also to check. Yeah, this one I wanted to check. Yes, so every single node maintains this state, and they, through the gossip protocol, they spread it around. Good. Now, as a basically ending of the stream, I would just solve the lead code problem, and you might ask any questions you have so far. I will not explain a lot. So previous time we solved longest common subsequence, I guess. This time is dynamic programming, and we're gonna solve this one. So yeah, I will be solving the lead code, and you're gonna ask any questions about the Redis shard, because we don't have time today to implement the POC for Redis hash slot sharding, our own one. So it will be the next stream, and yeah, this is basically the finishing. Shiva has many transactions. Okay, this is classical dynamic programming problem. It's knapsack take or not take. So how it is solved in general, we we keeping the index for every single day and price on this day, for every single price. And at every single index, we basically have two choices, whether to take it or not take it. And since we should maintain the state that we took already some stock, because if we buy stock, we cannot sell it. I think it's somewhere mentioned. Yeah, you may not engage in multiple transactions simultaneously. You must sell the stock before you buy again. So our state would consist of, I don't know, what should we return? Find the maximum profit you can achieve. So get max, let me name like this. So our recursive subproblem will look like this. We have index, and we have I don't know, bought or not bought already, and that will be it. So if index equals length prices, we return 0, because there is we cannot make profit anymore, right? And yeah, that will be it. So now, if this is not the case, we just check if we didn't buy the stock before, we can buy it now, or skip and not buy it still. So how it would look like and how it will be expressed in the code is like this. So we have answer, right, like this, answer equals 0. And first option is to buy today's stock by today's price. So it will be something like that. Okay, wait a moment. Can she complete matters? Okay, what are our constraints? Pretty high actually. Okay, we are still missing the information of how many. Okay, maybe I would do this other way around. Yeah, I would do it the other way around. It's not actually knapsack in a sense. So our choice would be, if we decide to buy today, we should straight away decide when we sell, and we iterate all possible choices for selling. And then basically, yeah, this is how we would do it. So let's say we are buying, and by buying, yes, so our money in some sense will become an index, yeah, like this. And we are starting from index in range, starting from next, ending at length prices. Money less than k answer is equal to 0. Yeah, and now our answer would be maximum from answer and money plus prices. This is kind of selling part at that point. Yeah, and then basically return ans. No, we don't return ans. It's gonna be maximum of this. Shit, no, we cannot do this. So if money plus prices is more than answer, only in that case no, we cannot do that. We cannot do that. Yes, exactly. Then result, we are first of all answer, we're gonna take like this. No, come on. I'm sorry. So if we at least profitable, so we gain some money, only in this case, yeah, I'm sorry, like I'm messing up. Only in that case we are going to do this. So we are taking maximum from answer and money plus prices it's plus get maximum starting from index and both. Actually we don't care. Yes, this is the recursion. Get maximum starting from index 0, or other choice might be to not buy it, and this choice actually we're gonna pursue, right? No. Yeah, now, so this is the part when we bought stock according to current price, and current price is price under index int, and we tried to sell it on the next days and initiated the recursive function call, a sub function in a sense. And this branch is when we didn't take the how it's called, didn't take the stock, so we didn't buy anything, and next day we can buy straight away. Yeah, let me actually try this code. Doesn't work. Wow. Of course. I don't understand why did I do that. So I could do just this. Exactly. Yes. Thanks for the stream. We'll be glad to watch something about Kafka. Okay, noted. Noted. We can check the queues as well. We can check the queues as well. So yeah, now let me check why this shit doesn't work. So I'll put it brackets just in case. So if prices, more than this one, then we're taking that profit and calculating profit for the next one, right? Can we sell and buy the same day? Fuck, I don't apply a transaction fee, come on. Yeah, we should apply minus fee here. Or actually we should apply fee here, minus fee, and this is minus fee. And in this case I feel like I need to do this profit, this guy, and if profit less than 0 we don't care, it will not maximize us, right? But if it maximizes us, we try it. Yeah, now it works. So this is basically, we can now do memoization on top of our DP. It should actually pass without time limit exceeded, and later on we can redo it, but it will be, or maybe it will not pass, because it will be n squared actually. Yeah, it will not pass. Yeah, so look at this. The thing is the topics, it's greedy. Yeah, I know the greedy solution here, but it is dynamic programming and it is as a multi-dimensional. So I think what they want from us is maybe to carry some other variable or whatever it is, right? So what can be our state in this case? Every possible index, we can either take it or not take it, but what other state we might take with ourselves? So maybe the current, how we can understand that we yeah, so what I'm thinking about that we need some second variable, like whether we already bought or not the stock, but maybe buy money. I don't know. Maybe this is how we can understand. And instead of this for loop, which will make it n to the power of 3, I guess, even. No, n to the power of 2n squared, I guess it can be, but not sure. Let me check the following. So let me check the following. So at every single step, if buy money equals 0, it means we didn't buy anything and we can buy it or no. So we can buy now and we should pay the fee already, right? So yes, so answer will be 0 and answer will be maximum of answer itself, get maximum index plus 1, and buy money gonna be prices yeah, and should I include fee? Fee is static, so we can include when we sell, basically, or we can include even now. So this is the money we spent beforehand, and also there's gonna be another choice to just move forward without buying, get max index plus 1 and 0. Else, if we already bought, we have also two choices, whether to sell now or to sell later. So our answer would be answer maximum, answer get maximum index plus 1. And how do we, yeah, if prices at this point minus buy money is more than 0, so if we are profitable, we do this. Yes, and we do exactly that. We should add this money. And now I put 0, we can buy again. Also, we're trying the case when we just keep bought stock and we hope we will sell it better next day. So this is gonna be represented like this. Exactly. Since fee is static, we can just carry it over every turn. And then buy money is 0, but this is pretty huge space to, but yeah, they are the same length and price, they're the same, so most probably it will be the same. Yeah, index. Yeah, it works. What if I put cash? Will it work now? But I don't think complexity changed actually that much comparing to previous solution. It's memory limit exceeded. What the hell? It's interesting. Now it's memory. Okay. And what if I do this cache and do typical thing if index by money in cache and return cache index by money. And native cache cannot handle this. If I do the following thing, will it work? Memory exceeded, this is interesting. That's interesting. Okay, so this is is interesting. I'm not sure what am I missing at that point. This is the greedy. Maybe instead of money, I can somehow propagate the kinda the index, but it will be the same. No. I can do like by index. And here I can state by money as prices by index. It's gonna be index, gonna be -1, but now I need to handle -1. Okay, I don't like this. Wait a bit, like how come this, like how come? The thing is that we cannot afford square here, because when you see in complexity power of 4, you cannot afford square complexity, but because it will become power of 8, and it is kinda not acceptable. Do we have? No, we don't have. So how would you else solve it? I don't see not squared solution, to be honest, so far. Aha, maybe there is greedy solution. But let's get back to the dynamic programming. So let's try greedy one. So I guess for greedy one we're gonna have this one and that one. Yeah, while right less than length prices. How we gonna do it? Prices left, prices right. So if right minus left minus fee is more than 0, we do that because, yeah, I guess greedily can be proved that it is a correct move. So our profit is going to be 0, and we just profit plus equals this guy, and then we moving left to the right, left to the right plus equals 1, and that's it. Else, if this is not the case, then we kinda moving no, we cannot do that, or can we? What if here would be, let's say, 4? Let me draw this example to prove formally. What if this guy would be 4? Then our profit wouldn't be 0, because 4 minus 1, 3, 3 minus 2, 1, so 1 we earned. And we are here 4 and 8. Minus 2 is going to be 2. No, this is going to be it. 4 plus 1, 5. Let me just run what will be this case. What the hell, what do you want from me, man? I just want to see the answer. Expected 8 still. Because this gonna have you 1. This gonna give you 4. Instead of 5. Then 9 minus 4, 5, 5 minus 2, 3. Yes. Yes, so our logic basically should be correct. If we have profit, we just do the profit and moving our 2 pointers. If we don't have profit, what will happen? Well, our left becomes right. Yeah, this is kind of exactly what we did already. Shouldn't be something like that. No. 7, 3, 6. Oh shit. Okay, it means that our greedy approach doesn't actually work. How come it's 7? This should be 0, so for 0 we just move forward. Oh, Katerina, thank you. Okay, I gotta be looking for solution, I guess, because I don't want to spend any more time on this. Consider first K stock prices. At the end, the only legal states are that you don't own a share of stock or that you do. Yeah, I really forgot how this thing is solved using greedy approach. I mean without the square, because why this still doesn't work? So 2, 8. 2, it's gonna be 4, right? Aha, okay, makes sense. Well, yeah, so I don't know how we can do it with how we can do it better than our stuff, our dynamic programming approach. Now I'm really wondering like why it didn't work. Oh my god, no, please give me some short thing. DP, where is the DP solution? Where is dynamic programming? Please give me dynamic programming. Is this a dynamic programming? I don't really see the dynamic thing here. Stupid shit. Okay, dynamic. I want dynamic programming approach, please. Oh my god. Why so short description of your explanation? Fuck it, I'm gonna use GPT. Give me purely dynamic programming solution using memorization. Hold on. Just hold on. So holding is actually, apparently this is Boolean, not the price. So we initially started with not holding, and if not holding, okay. And if holding, then we cannot hold and then apply. Aha. So we do accept the fact that we actually can basically go lower. I see. So this is pretty much apparently this is pretty much what we already implemented, right? So this was our trial of the dynamic programming with one dimension, but we were iterating every single recursive call. So it's n square, obviously not enough. In this case, let me just return our solution. And this is so bad, that the fact that we actually, oh, sorry. Yeah, this one. We actually implemented it in the right way, but the thing is that I was counting not that we bought or not bought, or didn't buy. I was using how much money did we spend on the buying the stock. So yeah, so instead of this by money, what we should do is whether we bought or not. So my initial thought was actually correct. And if we didn't buy before, in that case, what we should do? In that case, our answer is going to be get maximum. So if we didn't buy, it means we can buy now. So it means it's gonna be minus price under index, and we put here true because we bought, or we put false and carry over basically. Else, if we did buy beforehand, in this case, what will happen? If we did buy, what we can do, we can sell. First of all, we can sell. So if it's bought, selling means we didn't buy. And for selling, yeah, we are adding prices in the current index. Yeah, minus fee. Yes. Or otherwise, if we bought before, we can just move and keep going with our variable like this. No, let me change it like this. Yes. And initially we didn't buy anything. Checking. Checking. Yeah, now this is correct. Oh my god, why so hard? And now it passes, and you know why it passes? Because bot can have only two values. So now what are unique kind of combinations of parameters in our recursive function? It's starting from 0 to 10 to the power of 4, which is length of our prices, because this is our index. And second parameter is either 0 or 1. So it's basically 2 to the power of 2 times 10 to the power of 4, which is basically constant, can be eliminated in worst case. I think it can be even improved with the bottom-up approach. We can actually code it pretty quickly. So the p array, or sorry, cache, gonna be 0 times length of prices. Let me do +1. We know the worst case. So our base case is going to be this guy, 0. It's anyway 0, whatever. Yeah, and now what we do, so we started with index 0, so we're gonna start reversed. So for index in reversed range inline prices, and here we started with false, so we're gonna start, actually doesn't matter, both in range true, false. And now what we're going to do is to calculate, as always, we're gonna basically copy paste everything here. So yeah, we set our answer, and instead of this guy we just put in cache. Yeah, like this, like this, like this, like this, cache. Oh my god, without Vim it's so hard to modify these guys. Yeah, we are changing everything from the recursive function call to the accessing of the cache. Yeah, and also actually our cache is one dimension, so yeah, it's not how we want to do that. For in range link prices +1. What I want to do is this guy, cache append, and we want basically to do so let me name a 0 as a false and 1 as a true. So 0 false, 1 true. Great. And now yes, we kinda should do this main prices. It's anyway 0, so yeah, it should work. Good. So true, as I told you guys, or we can do like this. So true is 1, false is 0. And now we're gonna do, yes, so in this case true is 1, false is 0. That's it. And now we don't return anything, right? We just assigning cache index booked equals our answer, and in the end we return same thing like here, but cache 0 false. So cache 0 and false means 0 as well. Let's check this thing. Yes, it works. Let's check that. Time complexity should be much better now. Yeah, much better, but still the greedy approach, I guess, is somewhere here. So, but overall, yeah, this is task for 2DP. We don't care about greedy. That's it. Yep, that will be it. I think we should recap at the moment. So today we checked the Redis native sharding with the hash slots. We did a very great overview. Next time we're going to be doing proof of concept, POC of this implementation. So we're going to basically fork simple Redis based on .NET with the sharding implemented exactly like in Redis. So hash slots moving around, which will satisfy this thing that we don't rehash more than n divided by m, whereas m is number of nodes and n is number of keys. So that will be for the next stream. And for now, thank you all of you for being with me. Appreciate it. And see you next time, guys. Bye-bye.